Nicholas. I'm an undergraduate student studying aerospace engineering at the University of Michigan. This summer, I participated in an industrial program. I've been developing a MDO framework for M5. M5 is a student team at the University of Michigan. We design, build, and test RC airplane. We do it because we want to participate in the SAE Aero Design Contest annually. Well, it traces back to last school year when I was in the aerodynamics sub-team in M5. We spent a lot of time and effort conducting trade-off studies, and that's the main reason that I went to implement MDO in M5. A conventional design starts with a baseline design, then it proceeds to the analysis or experiment of different disciplines separately of the whole system. After that, subsystems are put together, and the performance of the whole system is evaluated. Designers will examine if the design is good enough to perform certain missions. If the system is not good enough, the design will be modified, analyzed, and then evaluated again and again, until the design is good enough. There are two issues for this conventional design process. First, it's really hard to find the direction of the modification of the design. The reason is that it's often difficult to find an explicit relationship between a particular design parameter and the outcome. This issue is especially problematic for designs with highly coupled disciplines. Consequently, a lot of time and work will be needed to reach the design goal. This is exactly what I've experienced with M5 last year. We have wasted a lot of time to do trade-off studies during the design process. Second, this conventional design process is generally not reaching the optimal performance. Due to the time constraint, designers will often stop when the design is just good enough for the mission. To solve these problems, MDO is more preferable. The MDO design process also starts with a baseline design. Then the whole multidisciplinary system will be analyzed altogether. After that, designers will evaluate the objective, which is a numerical measure of the performance of the design. We repeat the cycle until the design is optimal. Since we quantify the goodness of the design numerically, we can use computer algorithms to analyze, evaluate, and make changes to the design automatically until the objective reaches its optimal. This would greatly reduce the time and manpower in the design process. First I will show you this app. It's DSM, which is a standard design structure matrix. Right now I have 10 design variables, so in other words I have 10 degrees of freedom for my design. As you see in the boxes, they are representing different disciplines. They have different analyses within them. So the analysis and the evaluation go from one by one. First start with configuration, and then weights build up, static margin, coefficient of lift and coefficient of drag, and at last the one-way simulation. The outer loop will take care of calculating the objective, which is the weight of the payload, and the constraints to check if the constraints are violated or not. And also the gradients will be calculated, so the gradient provides the direction of the modification of the configuration. So code them using Open MDO, which is developed by NASA. Code them one by one, component by component, to see. This is the outer loop, and as you see, they're all coupled. I connect their parameters. Their outputs are some of the inputs of another component. So let's try to run the code. So I'll type opt.run here. And it will change the parameters, the design variables, automatically according to gradient. It usually run for like 5 to 10 minutes. It depends on the starting point, your initial values. Oh yeah, finally it's done. So this is the 2D video. As it iterates, it keeps changing the design variables, and the configuration changes accordingly. Alright, this is how it looks in 3D. It is an interesting result because we don't see finally often. In the future, I should add a dynamic component, dynamic discipline to do more accurate analysis. I think the most challenging part for me is to read and learn material that I haven't learned before. Since it's multidisciplinary, basically I have to know everything in order to model, in order to code the framework. So as an undergraduate, I think that's the most challenging part. It's fabulous. I've learned more about programming, about the concepts for MDO, and a lot of materials that I haven't learned in different disciplines. And I also love to work with Professor Martins. He's a really funny and easygoing guy. And in terms of flexibility, I can basically work anywhere, during weekends and after office hours. I will sometimes go to cafes to continue my project. Oh, and I actually have tried to work at bars as well. Yeah, it sounds weird, but it worked for me. Here I would like to thank Professor Martins for giving me such an interesting project. He didn't give me a lot of pressure and stress. Instead, he gave me a lot of flexibility and also a lot of laughter during meetings. I like it a lot. I really love this summer research experience.